When we left off last week, what were we doing?
The NAS and
stuff.
Right. NAS, aka SNAR.
Yep.
We looked at a reaction where we looked at a reaction where bromobenzene reacted with a nucleophile, and we didn't even pay attention to what the nucleophile was. But we said the most common nucleophiles were OH minus, RO minus, so oxygen anions, and then nitrogen ions, NH2 minus, NRH minus, NR2 minus. So, and we're going to look more at carbon ions later, but that'll be in our next unit. So we've got some nitrogen and oxygen ions. Then we spent some time doing the mechanism for the substitution of chlorobenzene. What compound did we get at the end? What is that compound? Two different ways you could name it. Common name and a systematic name. Not quite. It's on the right track. Good. Methoxybenzene. You said methyl oxide, James? Oh, yeah. Actually, even the substituent, we would just call it a methoxy substituent. Methoxybenzene, systematic name. And of course, that's because it's a methyl group attached to an oxy atom. But we could have ethoxy, isopropoxy, tert butoxy. But methoxy is also commonly called, anybody? Anisole. Its common name is anisole. All right. So we found that NAS can happen so long as there is a halogen leaving group. And we're going to pay attention mostly to bromine and chlorine. But I want to talk to you guys a little bit about the energy diagram here of what we're doing. Let's say that this is our starting material, a halogenated benzene, and this is our product, a different substituted benzene. They should have fairly similar energies. This is our energy diagram. On the x-axis, we put reaction coordinate. We're just showing where we are. Starting material, products. In order for this reaction to occur, we need to get into that high energy sigma complex. And that sigma complex is resonance stabilized. We saw that there were 3 resonance forms of this negative charge moving around the ring. And then a leaving group leaves and we go back down to lower energy. This takes energy to break aromaticity. Aromaticity is this stabilizing force in a system, so to destroy the aromatic ring requires energy. I kind of want to touch on what happens with different halogens, but I don't want it to be the biggest part. We're not gonna test on it much. If I compare the reactivity of fluorobenzene, chlorobenzene, bromobenzene, and iodobenzene, which of those halogens do you suspect will substitute the quickest? Which will be the most reactive? Is it the carbon-fluorine bond, which is the shortest and strongest bond, or is it the carbon iodine, which is the longest and weakest bond? Which do you think would substitute faster? Longest and weakest. That's the hardest bond to break. But it turns out it's not just breaking the bond that is hard, it's breaking aromaticity that is hard. So actually for the carbon-fluorine bond, the carbon-fluorine bond has the largest dipole, meaning the strongest partial positive on the carbon, attracting the nucleophile the most. And the carbon to iodide creates a smaller partial positive, which does not attract the nucleophile. So despite the carbon-fluorine bond being the hardest to break, that's not the rate-determining step. The rate-determining step is breaking aromaticity and then breaking the carbon-halogen bond. Here, we break aromaticity. That's why it is higher in energy. Here, we break the carbon-halogen bond. So it's less about what bond is being substituted, and it's more about how attractive the ring is to a nucleophile, how easy it is to break aromaticity. So we're going to look at some ways that we can actually decrease this energy barrier here and make the reaction occur faster. We'll refer to this as activation. If we can lower the energy barrier, we can activate the ring to react faster, and we'll call that activating. In order to do this, what do we need? Something that puts a positive charge on the ring so that something will come in and donate electrons there. We call these electron withdrawing groups. Also, we call them EWGs. Electron withdrawing groups pull electron density out of the ring, leaving the ring more electrophilic. These are things like cyanide, nitro, sulfonyl, and carbonyls. And those carbonyls can be a lot of things. Like that could be a ketone, an aldehyde, an ester, an amide, a carboxylic acid. A carboxylic acid is not great because we do want a nucleophile and we don't want to protonate the nucleophile. But in theory, anything that has this double bond. If you draw out those groups a little bit more, you'll actually notice that they all share something in common. Off of the aromatic ring, and I apologize, maybe I should have said that these are all attached to an aromatic ring, and we can abbreviate that as AR. All of these groups have something in common, which is that off of the aromatic ring, there is a pi bond directly with the atom attached. That's convenient. Because if you want to draw electrons out of the aromatic ring, they have to go somewhere. So they can get pushed into these pi bonds and held onto by those electronegative atoms. I can push electrons to the oxygen, to the nitrogen, to the oxygen, to the oxygen. So quickly, I just want to point out with one of these groups, I'm going to draw in the pi bonds of the aromatic ring. I'm not going to do a circle because I need to pay attention to those bonds. Does any one of these groups call to you the most? They all work essentially the same. It's just a different combination of atoms in the pi bond. Which one do you want to see exemplified? Elliot's got one. Come on. The sulfonyl group? Great. Do you guys remember my tips for how electrons move? If a bond breaks toward the more electronegative atom, If a bond forms, it's from the more electronegative atom. Well, if we're looking at this electron withdrawing group, this sulfonyl, I'm going to pay attention to one of the two pi bonds. And that pi bond will break towards oxygen away from sulfur. Yikes. Now sulfur is short on electrons, so where can it pull electrons from? It can pull electrons from the ring, because we have this 1, 2, 3 placement of atoms, that 3-atom system that allows us to do resonance. So I've drawn 2 arrows. Let's look at the resonance form that is generated. Can we agree that this is not the best resonance form for this structure? Because it maximizes charge. But it does point out to us that I can place charge in the ring. Specifically, I can pull electrons out of the ring and place a positive charge in the ring. Can you tell me what position the positive charge is in the ring relative to the sulfur group, relative to the sulfonyl group? Ortho. Right now, the sulfonyl group has placed a positive charge ortho to itself. Now I can draw another resonance form where we see the positive charge is placed para to the sulfonyl group. And for this reason, electron withdrawing groups activate the ring towards NAS. They make it easier for a nucleophile to get pulled into that positive charge. They're strengthening the positive charge of the ring. Electron withdrawing groups activate electrophilicity. They activate for NAS. But not on every position. They do a really good job at ortho-para positions. So we say in NAS, electron withdrawing groups are ortho-para directors. They're going to tell the nucleophile to attack ortho to themselves or para to themselves. Let's just take an example, and then we're going to do a mechanism here. One, 2-dibromo, 3-nitrobenzene. My electron withdrawing group, nitro. One of my bromines is ortho to the nitro. One of my bromines is meta to the nitro. When I react this compound, let's say with sodium hydroxide, one of my bromines will be substituted. Which one? They won't both be substituted because they're not both equally reactive. One is more reactive than the other. One is more activated towards NAS. Which one gets substituted? Let me say it a different way. What carbon will the nucleophile attack at? It will either attack ortho to the nitro group or meta to the nitro group, where the halogens are. Where will the nucleophile attack? At the carbon ortho to the electron withdrawing group. Ortho and para, yep. It has activated the ring ortho to itself. It has activated the ring para to itself. And so the nucleophile only substitutes at the position ortho. NO2, the nitro group, activated NAS, ortho to itself, not meta to itself. Why? It actually has to do with this. The nitro group has lowered the activation barrier. It has lowered the energy of the sigma complex. It has made it easier for a pathway to occur if it occurs at the ortho position. On your worksheet, you have something like this. This is in the middle. We start with, let's see if I can even name it. 1-bromo, 2,5-dicyano, 4-nitrobenzene. How many electron withdrawing groups there? And then I changed one of the cyano groups to a sulfonyl group. Sorry. Maybe leave it as a cyano group in the last two structures. I accidentally made the bottom cyano group a sulfonyl. I don't know how that happened. Out of the two cyanos and the nitro, how many of those are electron withdrawing groups? Yvonne? Cyano, electron withdrawing group? Yes. Nitro? Cyano? Yes. All three of them are electron withdrawing groups. What is the position of the nitro group to the bromine? How is the nitro positioned relative to the bromine? Ortho, para, or meta? Para substituted. How about this first cyano group adjacent to the bromine, related to the bromine as ortho? And the last cyano group, related to the bromine as meta. So I have 3 electron withdrawing groups. Not all 3 of these are actually activating the reaction. This will activate NAS. This will activate NAS because these are ortho-para substituted. This will not activate NAS because it is meta substituted. Now, what you have in front of you is the intermediates that are formed. Can you tell me what I drew as the nucleophile? No, you can't tell me? NaNH2, thank you. I'm going to ignore the Na. Are you okay with that? Sodium is the counter ion? Tell me.
What does NAS stand for?
Were you here last week?
Yeah.
Do you have this?
Yeah.
Okay, it means this.
Oh, thanks.
Do you want to read it?
Nucleophilic aromatic substitution.
That doesn't always mean anything to everybody. So do you guys remember the trick that I gave you on how to interpret nucleophilic aromatic substitution? What does it tell you about the reaction? Substitute, read it backwards. Substitute an aromatic ring with a nucleophile. Here's our nucleophile. Let's substitute the aromatic ring. I'm not trying to put the spotlight on you, Ella. That was a great question. It's a good review. Okay, our nucleophile will attack. What position does it attack? Where the bromine is. So nitrogen attacks at this position. I'll be honest, I don't know if I kept my resonance form the same as your resonance form. I did not. So let's draw this resonance. I'm going to change my resonance form just so that it agrees with what you have. I've said this before, and I will say it again. No two resonance forms are different from each other for benzene. They are the same, but they do have to be drawn. The arrows have to be drawn a little bit differently. Okay, our nucleophile attacks. That is going to break the pi bond in the ring. Where does that pi bond want to go? Well, it can go on to this carbon in the ring, but carbon holding a negative charge is not a good resonance form. So I am going to expand the nitrile group, and I'm going to show the nitrile withdrawing those excess electrons so that it doesn't have to sit on the carbon. Pi bond breaks to the nitrile, pi bond in the nitrile breaks open. This is a major resonance form. Why? Why is this a major resonance form? Appropriate charge placement. If I had not placed the pi bond into the nitrile, if I instead had placed a lone pair on this carbon, where's a better place to put a negative charge? Carbon or nitrogen? Nitrogen. So this is a major resonance form. It's not the only resonance form. We actually skipped one. Here's the deal. I decided during last semester not to have you draw every resonance form, but to ask you to draw the major resonance forms. You are absolutely allowed to draw every resonance form. I won't take points off, but I will assign points to my mechanisms based on you drawing the major resonance form. Here's a major resonance form because a more appropriate atom is holding that negative charge. But the resonance continues. This negative charge reforms the triple bond in cyanide. The carbon in the ring to the nitrile, that pi bond breaks back down into a pi bond, essentially moving over and breaks off the nitro, breaks off into the nitro group. So here I'm going to expand my nitro group. Negative charge on oxygen, positive charge on nitrogen. This pi bond in the ring is pulled into the nitro group, and the pi bond in the nitro group breaks off onto the oxygen. My electron withdrawing group has now withdrawn the electrons. Your electron withdrawing group has just withdrawn the electrons too. I skipped a resonance form where carbon held a negative charge because that's not a major resonance form. You're welcome to show it. If you watch my lecture recordings from the fall and the summer, you'll see it. But this semester, I'm going to show you just the major resonance forms. Why is it better to place the negative charge on oxygen instead of carbon? More electronegative, a more appropriate place. Okay, I see that I forgot my second cyanide group here. Okay, now I want to see if there are any other resonance forms that I can get. So I'm going to take this extra negative charge that is being held on my nitro group. I'm going to push it back in to form that bond. I'm going to push this CN double bond back into the ring to reform my carbon-carbon double bond. Is it possible for this other cyanide group to help pull electrons out? Well, there's a bond forming right here, as indicated by this arrow. That means that this carbon on the right is going to have too many electrons. It needs to get rid of some of its electrons. Can it break this pi bond down to the cyano group to help get rid of those electrons? No. That keeps the same number of electrons and just puts them in a different place. That would give it a double bond, and a single bond. That's 5 electrons. Remember that we said the cyanide group that is meta does not contribute to the activation of this reaction? This is why. The meta position is incapable of being involved in the resonance. Ortho and para positions, they are involved in the resonance of electron withdrawing groups, but the meta position, relative to my group that's being substituted, it can't be involved. So my only other step then is to reform aromaticity and break off the bromine. All right, I do see it now, why this is a challenge. Here's how many resonance forms we skipped. 1, where the lone pair was held on this first ortho carbon. 2, where the lone pair was held on this para carbon. 3, where the lone pair is held on the second ortho carbon. I skipped 3 resonance forms, and I still showed you, well, I guess just 2 resonance forms. So this reaction had a total of 5, and I skipped 3 of them because they were not the major resonance forms. They had inappropriate charge placement. But by shortening the resonance forms, do you see what I've done with my arrows? Good Lord, there are so many of them on each form. So this is a guinea pig test. I'm trying to see if less resonance forms is more useful, because it'll mean less drawings for you guys to do and less for you to memorize. But what you'll have to quickly identify are the ortho-para positions and recognize that those electron withdrawing groups will be involved in the arrow pushing. They will be involved in the intermediates. All right, coming back to this energy diagram. In black is what we did last week. Just the substitution of bromobenzene. It takes an amount of energy. In blue is what I showed you with this 1,2-dibromo-3-nitrobenzene. Having 1 electron withdrawing group decreased the energy of the reaction coordinate. Now I have 2 electron withdrawing groups that have both decreased the energy of my reaction coordinate and made it easier for my pathway to proceed. The more electron withdrawing groups, the more resonance forms, the more reactive the structure is. Does that make sense? The more resonance forms, the more reactive it is. The more resonance forms in the intermediate, the more stable the intermediate is. Resonance is a stabilizing force. So it makes it easier to get to that intermediate energy. Okay, well, here's what I want you to do with that. Underneath this, you've got 4 compounds. Take 5 minutes and rank these compounds from most reactive to NAS to least reactive to NAS. Talk with your neighbors as you go through it. Yes, sir. Ma'am. Yes. Here you go. I don't. They are on Canvas, but I don't have any on me.
No worries.
I'm sorry.
No, it's okay.
Yeah, he fights it too. You can always tell.
No, I feel so bad. It's like I've been here since like 7:30
The
in
more
the
resonant,
morning.
more.
On campus?
Yeah.
It's a long day. So by the time you leave, you've had like a 12-hour day on campus. That's crazy.
I know.
Hey, I've always said it, and I'll always say it. When students sleep in my class, I wear it as a badge of honor
Yeah, please do, because
that you
class I do.
you see this as a safe place to sleep, and that's good.
And there's gonna be a lot more to come.
That's good.
I think skipping resonance forms is not going to be my forte.
Okay, then I will encourage you to draw them all. So
If you
here,
draw them all, but you don't like do all of the arrows on the major forms. Like you know what I'm saying though, right? Like you show the steps, but like
yeah. Well, since I'm only grading you on the major resonance forms, yeah, I think that's okay. Ella, here are the resonance forms I didn't show you. Those are the 3 missing resonance forms.
Oh, so are we saying this, literally from the first part, are we saying that this is reacting with NH2?
Correct.
Okay.
NH2 is the nucleophile.
Because then, after all of that and all the resonance forms,
Yep,
bromine gets knocked off.
that's right.
Wait.
Sorry? No.
That's what I thought.
Good.
I was like, this isn't right.
What else did I give you?
Then I gaslit myself.
Oh, right, that's why I did this.
what about electron withdrawing groups with no leaving groups?
Where did I do that? No, there's leaving groups on all 3 of the structures.
Oh.
Or sorry, all 4 of them.
That's because I was.
That's the product.
I was like, you're lying. What my face?
That would be pretty rude, yeah. No, that's okay. Okay, did you rank them? Yeah? What is your most reactive structure to NAS? Most reactive. Do you know what? Let's do this. Let's label them A, B, C, and D. This is what I do a lot on exams. We'll do least reactive on the left to NAS. This is important because today we're going to talk about EAS. Most reactive to NAS. And we put A. Nope, we didn't. We put B. Can someone justify it? Please. Katie.
Has the most like groups that are able to react.
Can you
Has most like electron withdrawing groups.
good,
So increased electron withdrawing groups
good,
increases reactivity.
good. It has the most electron withdrawing groups. The more electron withdrawing groups, the more reactive to NAS. Did you want to add anything, Ali? Did you want to add anything, Peyton?
Nope, I think that was good.
Okay, what about our least reactive? Oftentimes it's easy to find the highest and lowest. Ooh, so it sounds like we're torn between C and A. Can I get a volunteer to discuss their ideas? Ozzy. So C, because the electron withdrawing group is meta, not ortho or para.
I say A because OH isn't an electron withdrawing group.
A, because at least sulfonyl is electron withdrawing, but OH is not electron withdrawing. And if it's the electron withdrawing character that actually improves reactivity, A doesn't have that at all. Does that change your answer, Ozzy? Good. So A is the least reactive because there are no electron withdrawing groups. How can we rank C and D then? Ozzy? No, this one is you. Meta versus para. Here I have the same number of electron withdrawing groups in C and D. One is placed meta to the leaving group, not going to contribute to resonance, but at least it does pull electron density away from the ring, whereas OH doesn't pull electron density from the ring. And CN is para, so it will be involved in resonance. So D, second most reactive, C, second least reactive. So what do we call OH if it's not an electron withdrawing group? Electron donating group. And in fact, this is the last note that I have for you guys on this, which is electron donating groups also called, you got it, EDGs. Oh no. They prohibit NAS. Not only is A the least reactive, I've been saving this energy diagram for a while. Here's what NAS looks like with an electron donating group. Oh, okay, I ran out of space. If it could happen and get to the final product, the transition state is up here a little bit. Oh, I touched it. Did you see that? Please, I work in a chemistry lab. I always wash my hands. There's nothing dangerous in that wall socket. Just dirt. Exactly. No, probably not dead bugs. Come on. Do you understand what I'm drawing with that red line? Just to break aromaticity becomes exponentially hard. So aromaticity just won't break. It is not impossible, but nearly impossible to do NAS when there's an electron donating group. So let's talk about electron donating groups quick. And this time, no, I don't want to put it. Here are some electron donating groups. I'm going to say NR2, but that can be the combinations of NH2, NHR, NR2. Peyton, did you have something before I get too far into this?
Yeah, I just had a question. The one, C,
Yeah,
since it is a meta position, will the reaction occur?
it will.
Okay.
Well, we know that the reaction occurs without it.
Okay.
We started by substituting bromobenzene.
It's just less reactive. Like it's not good.
Okay, good question. So bromobenzene is there in black. We could say that this is in blue. It is more activated. It requires less energy because this is pulling electron density away from the ring. It's just not exactly at the right positions, but it is pulling electron density out of the ring. And then in green, we could say this, where it's helping even better. It's really contributing to resonance. Ozzy? Here's something we could put in. We've got this list of A, C, D, B. Where does bromobenzene fall on this list? Peyton, your question is, bromobenzene will be more reactive than C because the sulfonyl group is not in the appropriate position to engage in resonance. But it's still an electron withdrawing group, so bromobenzene is more reactive than the electron donating substituted ring. But having any group improves reactivity. Having the group placed appropriately improves reactivity. And then having tons of groups improves the reactivity.
Okay, yeah.
Was that a good way of visualizing how they rank? This is the bare minimum. You have to have this. Okay. Here's my aromatic group again. Why is nitrogen electron donating? Well, it's got that lone pair on it, and it can actually push that lone pair into the ring. We noticed how all of our electron withdrawing groups had a pi bond, and those pi bonds drew electrons out. Here we've got lone pairs that push electrons into the ring. We can also have oxygen groups. Once again, OR, OH, anything. And once again, we have a lone pair that can donate into the pi system of the aromatic ring. So we have a donating effect. And then we have alkyl groups, carbon groups, methyl, tert, butyl, isopropyl. These are very weak electron donors. And in fact, these guys don't inhibit. And it's because they don't really have electrons to push into the ring. They can't contribute in resonance. All they have is like a little inductive effect. They have some electron density that they don't hold on to very well, that they're willing to push towards the ring, but they don't, a carbon group doesn't have a lone pair of electrons to donate into the system. So this is a weak electron donating group, and in fact, doesn't inhibit NAS. You won't see it very often. I promise I won't give you trick questions where I'm like, what's the NAS product? And it's like, trick question, NAS doesn't happen. So just for that clarity. All right, here's what I would like you guys to do for the next 5 minutes, and then I'll give you a 5-minute break. And that is predict the reagent that is necessary for this NAS reaction, predict the product that is formed from this NAS reaction, and then can you give me a multi-step synthesis that gives you this product? Start where it's easiest. Predict the reagent, then predict the product. Then start thinking about the multi-step synthesis. All of them on the bottom three. Oh, drawing the product. I'll give you a hint on the synthesis. Because there's technically way more than one way you could do it. This is what I want to see. 2 steps, 3 points, 2 reagents, 1 intermediate. What questions can I answer as you guys are working?
I don't even know where to start.
Find a reagent.
I don't even know.
Well, what do you need to get into your structure?
Something with nitrogen.
Okay, what does that nitrogen need to be bonded to?
2 carbons.
Great. Not just 2 carbons, 2 methyls.
Yeah.
Because it could be 2 carbons connected in a ring. That could be like a cyclopropyl type compound, but with a nitrogen. But it's not, it's 2 methyls. Think about how NaNH2 gave you an NH2 group.
So it'd be Na.
Yep.
3, 2, 2, 3.
Yep. Howdy. Good.
Is there a laptop left here?
Have you guys seen a laptop?
Gray Lenovo.
I didn't see it. Did anybody? You're welcome to look around.
Okay, sounds good.
Oh, here's one. Yeah, this is it. There you go.
Awesome, very good. Thanks,
Have a good
guys.
night. Yeah. Well, you never know with the conversations we can have in organic chemistry. I have had some classes where I would not have wanted that to happen.
Eventually.
Wait, okay, so are we drawing the resonance form?
No,
Does that mean that this reacts
no carbon here.
with NH2?
No.
What it was? Oh.
No, because if it was NH2 minus, it would end up being NH2 attached.
Would you have been mad if I said you're so right, bestie? Because that's what almost came out of my
No, you Gen Z, you have your own language. It's okay. I don't take offense.
Wait, but it was an NH2 minus on here.
Yes, and it left you with an NH2 on the molecule. Do you want NH2 on the molecule?
Oh, these aren't hydrogens. They're
That's
methyls,
right.
aren't they?
That's right.
Okay.
Perfect.
Are these
You added a carbon that
wasn't there.
didn't exist.
In my mind, I was like, yeah.
Wait, aren't these both methyl? You both said they were hydrogens until you were up there.
Huh?
You both said that they were hydrogens until you were up. Like, no, they're methyls, not hydrogens.
Oh, you thought the same thing?
Yeah.
Why? Every end and every bend.
I think we're used to like NH2. Like, oh, that's an N.
But then it would be written, I think, as
Yeah.
NH. I could see you thinking I made a mistake because I make mistakes. We're predicting components of our reactions. What do you guys think?
I'm personally kind of stuck.
Okay.
I know you need that.
Well, that's our starting material. You already have it. Oh, this.
As for the reactants.
Yes. Well, okay.
Because you need like not
Kind
that
of.
specifically, but like
Those are the atoms.
those have to be somewhere in it.
Sure. And actually, we already know that I don't want these 2 carbons and 6 hydrogens just randomly. I want them to be 2 methyl groups, and I want them to both be connected to the nitrogen. Let me give you guys this as an example. When we did the substitution with NH2, we saw that NH2 was the reagent. It attacked the electrophilic carbon. And then what we had at the end was an NH2 group. So if you want to know what your nucleophile looks like, erase the rest of the molecule and make it nucleophilic. Cut it off from the structure, you've got your nucleophile. And now the same thing goes in reverse. When you've got a nucleophile and you want to predict the product, just substitute the group for the nucleophile. Sorry, I did think this would be easy. It's just a little game of pick the puzzle piece off and identify what it looks like. And there's a lot of different ways to draw them, so there's no one right way to present this. Great. We don't need to show the negative if we show the Na counter ion, but I wouldn't mark points off for that.
Okay.
That is accurate.
Don't look at that one.
Good. Oh, I want to see it though.
I guessed. I don't know.
Ah, not a bad guess, but the bromine would go to the more substituted position.
Which would be?
Oh, actually, they're equally substituted. They're both primary carbons.
Yeah.
Mmm.
I figured heat helps.
Maybe? Okay. You're missing your aromatic ring.
Oh yeah.
Isopropoxy cyclohexane. There you go. It's fine for you. This is an interesting way to write the chemical formula, but I'd take it because it's all correct.
Why do we know? You just need the Na on there to balance charge?
Yeah, you could leave the Na off and just put a negative on the nitrogen.
Okay.
Absolutely. Because the Na doesn't do anything.
Yeah. Okay.
And you said that's an interesting way to write it. So what way would you want us to write it?
Oh, like NaNCH32.
Well, I wrote this first just based on what was it, and then I overheard you
Sure,
about how you did
sure.
it. I was like,
But I mean, strange ways of communicating structures are not wrong ways of communicating structures. There is a difference.
You're okay with this with chart, though?
Absolutely.
I don't really know how to do it.
Good. This one is okay, but this kind of hybridizes bondline and Lewis because there is an H
Yeah, there is an issue.
attached to that carbon, but you didn't show it.
Yeah.
So if you're going to show the carbon, it's a good idea to show the H too.
Okay.
If you don't want to show the carbon and the H, then assume the carbon as well. Does that make sense? Okay. Kind of like I did up there. I drew it as like the stick going to the O minus. Okay. Okay, what did you guys find? Great. That's a good start.
But this would have negative charge, right?
Yes. Or you could show it with Na in front, because that would imply that it has a negative charge. So just like you did, perfect. Now you're going to substitute the bromine, right? So instead of a bromine, there will be a bond to an oxygen, because the oxygen is the nucleophile. And the oxygen is attached to a CH, which has two CH3s attached to it. In fact, I have reinterpreted that chemical on the board. So if you want to see its structural drawing. But you don't need its structural drawing. You could literally write OCH3CH32.
So we're talking when it attaches to it first, it stays on there and then cycles through and then kicks off the chlorine at the very end.
This is SN2. But we're not doing an SN2 reaction. We're doing SNAR, which is that sigma complex intermediate. The resonance forms are generated first, and then the group is eliminated and substituted. Yep.
I forgot to watch the video for today, so like I don't know what you guys are saying.
And then it goes and it attacks. It doesn't attack this like the leaving group. It goes and it attacks the
Carbon,
okay.
and breaks the carbon-carbon bond into the ring, and that has resonance in the ring. And then a carbon-carbon bond reforms and kicks off the leaving group, an elimination step. So SNAR, otherwise called NAS, nucleophilic aromatic substitution, substitute, aromatic ring with a nucleophile.
Okay.
A nucleophile attacks an aryl halide carbon, breaks the aromatic ring. That's an addition step.
Okay.
And we get this high energy intermediate. And then elimination happens and the halide breaks off. That's addition plus elimination, substitution.
But wouldn't it take a lot of energy to make it unstable by breaking them?
It does. And we can actually lower that energy by adding groups into the resonance intermediate that hold that negative charge better. First, they pull electron density out of the ring and they leave a bigger partial positive, so a stronger attraction for the nucleophile. And then they stabilize the intermediate, which means it activates the reaction. It lowers the activation barrier. So we call those electron withdrawing groups. Electron donating groups will prohibit this reaction because they make it really hard to break the aromatic ring, except for alkyl groups, just carbon groups.
So is NH2 like the electrons withdrawing?
Yeah. Yes. Oh no, NH2. Where? Like here is the nucleophile. Actually, by the time the substitution is done, we don't have a withdrawing group. We have a donating group.
Okay.
So I gave an example earlier where 1,2-dibromobenzene reacts with hydroxide and gives us a substitution specifically at the ortho position. Do you guys understand why this reaction cannot go through a second NAS? There's a second bromine. Why can't it also be substituted? Now that we've substituted, we've put an electron donating group on. So the second bromine is there for good. It can't be substituted further because now there's a donating group.
Is this supposed to be a K or is that supposed to be an E?
Where?
So this one over here.
K.
Yeah.
Because the K means that the oxygen is negatively charged. All right, let's go through them, shall we? What reagent do I need here? I need dimethylamide. So you could draw that as nitrogen with two methyl groups coming off. You could write that as NCH3 with a negative charge. You could write that as NaNCH3 Na is a counter ion that tells you nitrogen is negatively charged. You don't have to show the sodium counter ion, but you can imply the charge on nitrogen by showing it. Here, my nucleophile is the oxygen. Now this was given to you as OK. The potassium is just a counter ion which tells you the oxygen is negatively charged. Is there a covalent bond between oxygen and potassium? No, it's ionic. So seeing potassium tells you you've got ions. I actually had a good question. Someone said, was this meant to be OH? No, because that is not a strong nucleophile. OH is a covalent bond, which means the oxygen is not negatively charged, and that is not a good nucleophile. But OK is ionic, gives oxygen a negative charge, is a good nucleophile. So this means that my product is isopropoxybenzene. Isopropoxybenzene. All right, this multi-step synthesis. Here's what did anybody come up with some? I saw Jackie's. Anybody else come up with one? Can I see it?
Yeah.
That looks like one step, though.
It does?
Yeah, yeah, it does. Anybody else? What'd you do?
Well, just have the two carbon groups,
Okay.
an oxygen, and an anti-Markovnikov HX.
Okay.
On there.
And that's actually what Jackie did too. I think the issue with trying to add an ethyl, like ethoxy, and then do radical halogenation is it's hard to control where the radical will form and how to get the the bromine on this position.
This is kind of like like when we had triple bonds that we added on.
You could. Now I don't want a triple bond because I don't want to have to do 2 steps to do 2 things with that triple bond. In fact, if I have an alkene intermediate, then I can do HBr anti-Markovnikov. The only problem with yours was that you just had a carbon chain, right?
Oh no, we would try to do the double.
Oh, yeah. Okay, so if you have this double bond coming off of your oxygen, now you can do anti-Markovnikov HX addition. So what reagent do you need to substitute the bromine for this vinylic ether? You remember what vinylic means?
Oh, because it needs to go onto the
Vinylic attached to the alkene. Well, just like last time, here's my oxygen nucleophile, here's the carbon group. Here's my nitrogen nucleophile, here's my 2 groups. Here's my oxygen, here's the group that it needs to be attached to. I've got this alkene with O-, and there's my nucleophile.
How come we just wrote it as 1 step?
Because I was showing a multi-step synthesis happening from starting material to product without clarifying how many steps were needed. Okay, let's take a quick break. Yeah, let's do like 5 minutes and come back at 6:15. What? Why is that funny? Oh. Oh, good. Let me see.
No, I just did it like this, but it had to be this hydrogen for some reason.
Oh, you're kidding. It was specific about which hydrogen
Which
it was.
hydrogen you did it to?
Wait, something's wrong about those arrows though. And and now I can't zoom in on it. Don't you feel like those?
The correct answer.
Don't you feel like those are the wrong?
Yeah, that's why it's taken me 25 attempts.
Oh no, here it is drawn right.
Oh.
Well, on mine, when you zoom into mine, which I got correct. No, I
Yeah,
got
that's
it
also the
out.
same.
I had to
But it
change
is-
which hydrogen it went.
Okay, let me ask you this. Did you have it attacking this hydrogen and then this CH bond breaking? Or did you have it attack one hydrogen but break the other CH bond?
This and then that.
Okay.
Can you look at your previous sentence?
Sometimes. It gets really hard to,
I don't even know how to do that.
and you can't re-establish it either, huh?
It was just being annoying.
That is really annoying.
I think I had to put that one in ChatGPT.
OH, and it only accepted it if you separated the H from the oxygen.
I'm pretty sure
Took
I
me down
used
to
ChatGPT.
6 attempts before D helped me figure that out.
For 14?
It wanted you to break an OH bond.
Well, not break it, just like how it was.
Oh,
instead
show.
of OH together, it was O bond H.
Oh, this is such a...
That's annoying.
Oh yeah, there was a couple in there that were like actual reactions, and I was like, we did not do like putting. It was like the benzene rings, and then it was like, what do you need to make an OH in here?
You know, guys, I forgot to tell you that active has practice problems. And it actually wouldn't have helped much if I had told you, because I found out last night in OCHEM 1 that I have to publish them. I thought that they just would come published because they're just practice. I don't assign them. So there's extra active practice problems for you. Sorry for the delay. Is this Lily, are you doing chapter 16 or 15?
The one you just decided that was due yesterday.
Okay, okay.
There you go.
So this is gonna participate.
This isn't the answer. This isn't how you're supposed to draw it. Oh, that's what pissed me off. Because in order to submit it, you had to have O to H. This is stupid. This is, I have this all. Whatever. See, like, look at my submission. It has it going to the hydrogen with another bond. But if you view how they wanted it submitted, when I submitted that.
Okay, so Lily, this is what you showed. Attacking the hydrogen on the right.
Yeah.
Let's see it. I don't know.
Why? Did she like do the exact same thing twice? So they said yes one time and no.
Okay, but is it possible you did this by accident?
Maybe we did that.
There was one time where we're like, well, maybe it's just being stupid. We played with it like that.
Okay, or the other thing that I would think is if you did this.
Yeah, we didn't do that. We went to a carbon.
Okay.
For one of them, I mean,
That is weird.
Do that. It has to.
Right, it would break the octet rule. Yeah.
It's like if you scroll down, the next part is the positives on the carbon.
On that same problem?
Yeah. So like you gotta keep going and add more arrows.
Like a resonance form.
Yeah.
Yeah. All right.
Oh, do you know Andy's in the Olympics?
Yes. Not in the Olympics.
Her sister-in-law there.
She got bronze.
Really? Okay, you know what? I told my partner that at the gym last week. I was like, I've got a student that's watching the Olympics in Milan. And he goes, oh, what is her sister-in-law like competing in? And I said, I don't know. Did I miss you? Oh, I handed it to you upside down. Sorry. You're welcome. Luge. Yes.
So for these, is the electron arrows basically breaking from NA to this one, and then that would connect over? Does that make sense?
No Na to N bond.
Right. Okay.
Yep.
Okay.
That's ionic.
They're ionic.
Okay. So no bond. Instead, just forget that Na exists and show it as N minus.
All right. I do like star nodes. Okay.
Good.
Okay.
Good.
Thank you.
Absolutely. And we'll come back to that as much as we can. How about here?
So for this one, you wouldn't show that break, right? You just show it connect over.
Because it doesn't exist. Yep.
Cool.
Yep.
Okay.
It's like saying to put on my shoes, I have to untie my shoes from each other and then put them on each foot. Oh, but my shoes aren't tied together, right?
Okay.
That was a weird analogy. It's just off the top of my head. Yes, you're welcome. You're welcome.
Thank you.
Wow, I cut it close today. How was Steamboat? Yeah, I bet. Yeah. Oh, you canceled your flight?
My flight was $60, so I just didn't.
Yeah. How do you get a $60 flight to Steamboat?
To Denver. Because I was going to meet people. Other people were flying to Denver.
Ah.
So I went to Denver, flights are always really cheap.
Mm-hmm.
And that's like without the bags. And it's like, bags would have been more than gas. Plus the time insurance, so I was like, oh.
Smart. So a fun fact, as we get back into things, this is on Canvas, and this was the first worksheet that I put together for my class last fall. And so earlier I was mentioning if you want practice drawing all resonance forms, this is a good one for that because it has you identify, are you looking at the ring as a nucleophile or an electrophile? What type of reaction is happening? And then it has you draw all of the resonance forms that exist. What I'm going to try and have you guys do this semester is use less resonance forms and focus just on major resonance contributors. So this is a resource for you, but I'm not going to go through it. Did we have remaining questions on NAS? Did things get clarified? Identifying nucleophiles, predicting how they attach, thinking about synthesis problems. Was this a nucleophile? Oh, I don't have a name for it. It's a negatively charged oxygen attached to an alkene. Well, you know what we could call it is like ethylene oxide, but ethylene oxide is the name of this epoxide. So that wouldn't be a great name. I think we could call it ethynyl oxide because this is an ethene group. Ethene, 2 carbons, alkene. Ethynyl oxide. And that would distinguish it from ethene. Ethylene oxide. Ethylene oxide, thank you. And you know what? I am thinking about this. For reasons that we'll talk about later in the semester, maybe that was a bad synthesis. You guys might recognize that there's a resonance form of that structure that puts a negative charge on carbon. And which resonance form is more likely to share electrons? Does oxygen share electrons better or does carbon? Carbon shares electrons better. So for reasons I don't really want to get into, this might have actually been a bad synthesis because of the resonance contribution of that group. Not doing this synthesis. That's what I would recommend is better. All right. Quick reminder, what did we just learn that aromatic rings can do in NAS reactions? Resonance? Yeah, the intermediate has resonance, but the ring can behave as what? One more time. The ring did not donate electrons. It what? It did kind of behave like an alkene, but not a normal alkene, because a normal alkene doesn't reform its alkeneness at the end of the reaction, right? So it did get opened like an alkene, but then it closed again. It like lost its aromaticity, it regained it. What role did it play in the reaction in NAS? It acted as the nucleophile. No. No. What role did it play? Whether it...
I would say, like, if it was, like, the stability, like, that's kind of what I was...
That's not a role. The ring was not the leaving group.
Electrophile, right?
The ring acted as the electrophile.
Yeah.
Well, it'd have to, because if the nucleophile is going to...
Right, right. Because we substituted the ring with the nucleophile. So what is the ring's role? Electrophile. Okay, so that's it. Halas, right? The ring can only accept electrons. It's an electrophile. No. The ring can also be a nucleophile. So what do we call this? If the ring acts as a nucleophile, we call it electrophilic aromatic substitution. Why? Because the ring is acting as an electrophile? No, whoever named these named them backwards. This is the EAS reaction. And in the EAS reaction, you substitute, say it with me, substitute the aromatic ring with an electrophile. Good job. People don't normally say it with me. So it's in the name, it's just backwards. What role does the ring play here? The ring acts as a nucleophile.
See, now that's what we were saying.
You were telling me in NAS it acted as a nucleophile, but it didn't. So NAS substitutes the ring with a nucleophile. Here, we'll substitute the ring with an electrophile. If that's the case, then the ring has to act as the nucleophile. So we have two opposite reactions. NAS, the one we just finished. The ring has to accept electrons. Okay, well, to accept electrons, it'd be good if that ring was more positively charged, more partial positively charged. So put groups on the ring that pull electrons away from the ring and towards themselves, and leave the ring as a better partial positive electrophile. Now, on the opposite hand, we're venturing into EAS, where the ring needs to be a nucleophile. So put groups onto the ring that push electron density into the ring. Make the ring more negative so that the ring can attack using electrons. So I'm going to preface this because we're going to spend time today and Wednesday on it, Thursday. The reaction we just finished and the reactions we're going into have exact opposite effects. And so what is true of one trend in NAS, the exact opposite is true of one trend in EAS. Electron withdrawing groups improved NAS. Electron withdrawing groups weaken EAS. They are opposite reactions, so the groups have opposite effects. First, I want to take you through all of the EAS reactions. We have 6 of them. We are going to learn the mechanisms for 4 of them. First, bromination. We'll react the ring with Br2 and a catalyst, iron 3 bromide. Do you know what I love to do on tests? I like to put a multiple choice question that says, which reagent completes the reaction as shown? And then I show Br2, Br2 in alcohol, Br2 in light, Br2 in FeBr3. I know. I do, because they do very different things. Br2 does not react with the aromatic ring. Br2 does react with alkenes, not with the aromatic ring. Br2 in alcohol does not react with the aromatic ring. Br2 in light does not react with the aromatic ring. Br2 and this catalyst, iron 3 bromide, will react with the aromatic ring. We're going to look at why it does in the mechanism. Chlorination, Cl2 and aluminum trichloride, AlCl3. In terms of mechanisms, these two are nearly identical. The only difference is whether chlorine is involved or bromine, and whether the metal is iron or aluminum. Other than that, all of the arrow pushing, all of the intermediates, identical. Okay, some more fun groups. We can do alkylation. What I am going to show here, I've written it on there as R. I'm not going to show it as R. I'm going to show it as tert butyl chloride with AlCl3. But this is to represent a specific R group. It could be any R. And what we mean by that is an alkyl group, just a carbon chain, alkylation. This is named after 2 dead men in honor and memorial of Friedel and Crafts, not Crafts of the mac and cheese fame. I know, I think that's a K. And you know what? I think I spelt Friedel wrong. I think it's EL. The vibe's right? The vibe is right. Every time I write it, I'm like, it's LE. And then I get away from it and I look at it and I'm like, I think it's EL. I don't know, that looks wrong too. Alkylation is the more important of those names, to be honest. Now I want to point out that this same alkyl group, the same R group, can actually be accessed a different way. We could also use this alkene in the presence of an acid, H+. You know how alkenes behave in the presence of an acid. We talked about it a lot in OChem 1. Alkenes in HCl, alkenes in HBr, alkenes in H3O+. What do they form? A carbocation. So the fact that this reagent and this reagent give you the same exact tert-butyl group product tells you the intermediate of both reactions likely involves a carbocation. Okay, similar to Friedel-Crafts alkylation, we will see acylation. What is an acyl group? An acyl group is a carbonyl. Again, Friedel-Crafts acylation. Acyl is the CO double bond. That's what we're getting at. I do want to point out that this is going to either give you ketones or aldehydes. Predominantly, that is what it's going to give you. Do you know what that functional group is in the reactant? The carbonyl bonded to a chlorine? That is not a ketone. A ketone has a carbon on both sides. It's not an alkyl halide, because an alkyl halide is bonded to an sp3 hybridized carbon. This halide is bonded to a carbonyl carbon. Did you have one, James? This is called the acid halide, because it looks like a carboxylic acid has been replaced by an acid halide. By a halogen. In fact, I want to take a minute to tell you guys something that you're going to see on active. And this is a reaction that we're going to come back to later in the semester. Thionyl chloride is used to convert carboxylic acids into acid halides. So if you don't have a carboxylic acid, if you don't have an acid halide, you can make an acid halide. This should feel familiar. It resembles the substitution of OH on alcohols using thionyl chloride. And in fact, the mechanism is very much the same. Oxygen attacks sulfur, chlorine gets kicked off, and chlorine attacks the carbonyl to substitute the OH. Okay, but of course, Friedel and Crafts are famous for using acid halides, but similar to their alkylation, this reaction can also be done using an anhydride. This is the acid anhydride. It's like two carboxylic acids less a molecule of water bonded together. Acid anhydride. So acid halide or acid anhydride, alkyl halide or alkene and acid. There are two different routes for these syntheses, and I will lean into the ones that are on the diagram more, but you will see some others on active that use those other reagents. It's useful to be able to practice with both. Last two reactions. Nitration, let's do sulfonation, H2SO4 and H2SO4 and SO3. This gives us sulfonyl groups. This is what we refer to in the chemistry lab as fuming sulfuric acid. H2SO4 in its pure form will vaporize and decompose into water and SO3, sulfur trioxide. If you have sulfur trioxide and water, they can recombine and form sulfuric acid. So we'll use fuming sulfuric acid as the source of this SO3. Okay, last one, nitration. We use HNO3 and H2SO4. How many of you did this in lab 2 weeks ago? Nitration of methyl benzoate. Concentrated nitric acid, concentrated sulfuric acid. This adds our NO2 group. In these 6 reactions, there are 2 families of mechanisms. The halogenation family, which we will be learning, and the carbon group family, which we will be learning. We won't be going through the mechanism for nitration or sulfonation. Is it because they're too hard? No. What's more relevant, though, are these mechanisms. And if you can get halogenation and carbon group mechanisms, then you can figure out the sulfonation and the alkylation. Question: what is being substituted? We're calling this a substitution reaction. NAS substituted a halogen. EAS is substituting hydrogen. Substitute an aryl hydrogen. That's what we're doing. It's actually kind of interesting. Sulfonation is the only reaction here that preserves the hydrogen. You can see that we're reacting with SO3, and I end up getting SO3. So the H from the aromatic ring tags on to the SO3 and becomes SO3H. Let's talk a little bit about byproducts. Catalyst FeBr3. Reactant Br2 only gives me 1 Br. What's my byproduct? Nice. That was like stereo. HBr. HBr is one of our byproducts. What about in chlorination, byproduct? HCl. What about in alkylation? HCl. Or if we used a bromine, HBr. We'll use chlorine mostly. What about in acylation? HCl. Gets a little repetitive. Nitration, no byproduct. Or sorry, sulfonation has no byproduct. Nitration, H2O. Good job, Belen. One of the oxygens from nitric acid leaves. One of the hydrogens from nitric acid, the hydrogen from nitric acid leaves. And the substituted hydrogen leaves. So we get H2O as a byproduct of nitration. Good work. Okay, I want to point out something about your homework, your written work, because I do want you to start thinking about it soon. I have updated the homework file. I updated it this afternoon, but I need to update it again because I didn't put in there show the major resonance form. I think what I said was I didn't really specify resonance forms. What I'm looking for is that you show just the major resonance forms. You have a mechanism on EAS. You have a mechanism on NAS. You can finish the NAS mechanism today, tomorrow. We have synthesis as well, but you'll notice that these synthesis problems are, it may be hard for you to notice. These are pretty much all EAS synthesis problems. So a lot of your written work can't be done with the information we have right now. So we still have a lot of ground to cover. And I know it's going to have to be split between today and Thursday. But I want to encourage you to do as much as you can before Thursday, or at least look at the problems before Thursday, so that when you come in, you're kind of looking for the answers to that homework. That way you can try and finish it Thursday, turn it in Friday so that I can grade it and give you feedback, because you have a unit test this weekend where you'll have to show a synthesis and show a mechanism. So I want you to be practicing, yeah? And I know the time is short on that practice. Unfortunately, all of the work for the written work comes now, at the time right before we begin our unit test. Okay, so underneath this, I've got activation and direction. We have already talked about this with NAS, so this is a bit of a review. But remember earlier I said NAS and EAS are opposite reactions from each other, so they're going to have opposite effects. I want to talk about first activators and deactivators. Because of course, I might not always start with benzene. I may start with phenol. I may start with aniline. I may start with benzoic acid. There's a lot of different substituted compounds that I may start with. So these compounds can activate the ring and they can deactivate the ring towards towards EAS. Now I've got this first diagram for you that shows alkyl groups. How did I orient it? Yeah, I did it the worst way I could have, okay. Alkyl groups, nitrogen groups, and oxygen groups. We know that these are electron donating groups, which means that they are activators to EAS. They make the ring a better nucleophile. They give their electrons to make the nucleophile better. In the second structure, I just have X. We're going to think of our halogens as their own compound, their own group. These are deactivators. By the way, I'm going to come back in and fill in something about the directing effects. Halogens do not give electrons to the ring to make the ring better as a nucleophile. Halogens pull on electrons from the ring, and so they make the ring less reactive. And then we have our nitro groups, our nitrile groups, our sulfonyl groups, and our carbonyl groups, our acyl groups. These are the electron withdrawing groups, and these are deactivators to EAS. If they make the ring a better electrophile, because they're good for NAS, then why would they be good at making the ring a better nucleophile for EAS? Doesn't it make sense? Okay, I'm glad. I hope it actually does. Okay. Much like our electron withdrawing groups had activating and, had these specific directing effects, these groups can also have directing effects. Electron withdrawing groups in our NAS reactions, they were ortho-para directors because at the ortho-para positions, they could be engaged in resonance. At meta positions to the leaving group, they could not engage in resonance, so they can't stabilize that intermediate, so they direct substitution ortho-para to themselves by lowering the activation barrier and making that pathway more likely. The same is true for our electron donating groups in EAS. These are ortho-para directors in EAS. They will stabilize the intermediate if the intermediate is substituting ortho and para to themselves. They cannot stabilize the intermediate if the group is being substituted meta. So by lowering the activation barrier for substitution ortho and para, they make that the most likely pathway. Not to mention, they are the ones lowering the activation barrier anyways. So if we have some combination of groups, let's say I have an alcohol and I have a nitrile, the nitrile is trying to increase the activation barrier, but the alcohol is decreasing the activation barrier, meaning the alcohol will guide how the group is directed. Halogens are ortho-para directors. And electron withdrawing groups are meta-directors. I do want to point out, with our last reaction, NAS, electron withdrawing, activators, electron donators, prohibitors. The reaction won't proceed. That's not true for EAS. In EAS, electron donators are activators, electron withdrawers are deactivators, but the reaction can still happen. If you have multiple substituents on a ring and they fit into different categories, we can still predict which one will direct the substitution. It's based on their activating power. So direction follows activation. Our strongest activator, should have done that in a different color. Our strongest activator is the one that stabilizes the intermediate the best, creates the lowest energy pathway for the reaction to proceed through, and has the overall say in directing effect. So I want to ask you guys quick, oxygen or nitrogen? Which one do you think is a better electron donating group? Got one nitrogen, one oxygen. More nitrogens. Does that sway you at all, peer pressure? Do you want to give your rationale?
I just know that oxygen can hold like electrons better.
Oxygen can hold electrons better. But am I asking about holding electrons? A donator has to share them. Why does nitrogen share electrons better? Less electronegative. So our activators actually go strongest at nitrogen, second strongest at oxygen, and then those carbon groups are really just like the little brother of the family. These are the weakest activators, but they are stronger than a halogen and stronger than an electron withdrawing group. There is a way to rank the electron withdrawing groups. We're not going to get into it. Not that it's not relevant. It's just not as meaningful to us as our strongest activators. We're usually not looking at multiple deactivators, wondering which one deactivates the least. We're looking at multiple activators, wondering which one activates the most. So we already know how this works. We can look at benzene and a reagent and look at a product that goes on. But what happens when we look at aniline and we do chlorination? How will the chlorine be positioned relative to the nitrogen? Do I have equal chances of having ortho, meta, and para substitution? No. Because the nitrogen can stabilize the intermediate if the chlorine goes ortho or para to itself. The nitrogen cannot stabilize the intermediate if the reaction is meta, and so the nitrogen favors the ortho-para direction. Two different products produced, ortho-chloroaniline, para-chloroaniline. Deal? It activated it, ortho and para. Now let's draw an energy diagram for this to show why the meta position didn't form. Here's my starting material. And here is chlorination of just benzene. Okay, that's if I'm just doing chlorination of benzene. As soon as I add this nitrogen group on, my activation energy decreases. The ring has been activated for the reaction. It takes less energy. But this intermediate only happens when it's being substituted ortho-para if the ring were to react in such a way that it tried to react meta. This is my meta intermediate. It's higher in energy still. Yes, it is more stable than just benzene alone. It is still activated, but it would take more energy. How is the ring more likely to react? It's more likely to react through the lower energy pathway. So I have this favoring direction for ortho and para. Do I have the time for it? No. What I'll try to show you guys on Thursday is why electron withdrawing groups on an energy diagram like this prefer the meta intermediate because that's lower in energy than the ortho and para intermediate. So that's where we'll pick up more energy diagrams, mechanisms, synthesis. You might, with this information, you might already have a way to dig into the multi-step synthesis problems on the homework. Take a look at them tonight if you can. Take a look at them tomorrow. Set a reminder. At least look over them and see what you can brainstorm before class on Thursday. Thank you for your time, guys. Have a good night.